It's really great to be here. Honestly speaking, it's a little bit twofold because on the one hand side, it's very sad for me to be here, to be honest, because when I heard about Agile meets architecture the first time, actually it was Stefan who told me in Budapest that I should join here because I work on this intersection between organization and architectural things for quite a while. So I'm happy to be here, but on the other hand, it makes me really sad, to be very honest, to be here with these circumstances now. But I will try to still cover the point in a way how I usually cover them. So I will try to make it as entertaining as possible. And as I said before, I'm David. So first things first, I'm actually coming from Vienna, but I moved over to Munich a few months ago, which also made obviously my traveling to here a little bit more complex because I usually just went to the plane, got to Berlin, and it worked very smoothly. This time I went by Deutsche Bahn and it worked not so smoothly, to be honest. I would have expected it differently. So when I'm in Germany, it's far easier to me to come to Berlin, but nevertheless, yeah, great to be here now. I work usually as a coding architect. That's how I call myself. Yeah, my official role is principal engineer, but I like, this kind of role where I do a lot of conceptual work, do strategic work, but also sit down together with the teams, and help them delivering software, help them in building resilient systems and stuff like that. And as I said before, I work a lot on the intersection between organizational perspectives, architectural perspectives, socio-technical things, we call it today. And I would say my whole reason to exist is basically, I would say that the main problem we still have in our industry, and the main problem we still have in our industry is very obvious. The more people we put on stuff to build stuff, the slower we get, right? If you ever worked in a startup, if you ever founded your own startup, if you ever talked to startup engineers, they usually tell you, hey, we started as 5 people, now we are 50 people, and it feels that we don't get that much delivered anymore as we got delivered with 5 people, right? And beside this also, the error rate, the down rate of a system usually increases. So things get massively complex, right? You get calls at 2 o'clock in the morning because something is down. And basically that's all what we want to avoid, because in the end we want to safely and sustainably reduce the time to thank you, how the North tends to say very well, I think. So the whole reason for existence for me in this industry, so to say, is basically to get a little bit more into this green direction, how Martin Fowler usually calls it, the design stamina hypothesis, right? And let's start the story first before we go into this whole aspect of cultivating architecture in agile environments. How it usually starts, and I don't have to tell you this, right? You're obviously in the industry also for quite a while, is that we have those simple systems, right? We have a couple of people working on that. It works out well. System grows. We get, value out of the systems. We probably will even get money out of the system that we can keep on working and working and working. And in the end, we end up in a complicated system. I wouldn't yet call it a complex system, but it's usually a complicated system, right? And this is where we start to see the work. And there was a couple of lovely sessions in the morning which elaborated on what is architecture actually about, right? Why do we need it? Why does it even exist, and so on and so forth. And it is, in the essence, it's about structuring, finding abstractions to make things more easy. Our whole industry is built up on abstractions, right? No other industry introduced so many abstractions as we did, right? All those things which we draw here usually, they don't really exist, right? If you open your phone, you will not find, the architecture somewhere nailed in, right? It's just, it's just built in our industry over decades now. And there's one thing which I want to bring in because I think it's so important, and it's such a misunderstanding we had over the last couple of years in our industry, that we of course need this modularization, and usually we ended up in distributed systems when we did this modularization, yeah? Am I a big advocate of distributed systems? We will talk about this in a minute. But the thing is that for modularization, you usually don't need distribution, right? Because these are 2 different axes, I would say. We have modularization, which can be well or bad, and we have distribution, which can be monolithical or which can be distributed. And what we usually have, or not usually, but very often have, is this big ball of mud. And I'm here with Joseph Joda, who says that unfortunately, architecture has been undervalued for so long that many engineers regard life as a big ball of mud as normal, right? And I think that's fully true. Yeah? The answer was, unfortunately, that we said, okay, we need better modularization, so let's go for distribution, which led us to distributed monoliths, we all know. And the proper answer is probably that we should probably go to something which we tend to call a well-structured monolith these days. And there's a lot of good points, right, to go for distributed systems, but modularization is none of them. And as Simon Brown phrases it much better than I do, if you can't build a well-structured monolith, what makes you think microservices are the answer, right? And I will talk about distributed systems for probably the rest of the talk now, and that's why I would like to dive a little bit deeper into this, why we basically then all go for distributed systems, right? And I'm fanatic about distributed systems, I would even say. I work on distributed systems my whole life. So what is the reason to go for distributed systems if it's obviously not modularization? Because we can also modularize quite well on a single deployment unit. And there are multiple reasons, right? I usually group them into two groups. The first one is the more technical group. And we all know this. We all know this from Sam Newman's microservice talks, right? We say, okay, we want to have independent scalability. Means, okay, we can have here 10x traffic, but on the other side of the system, we have usual traffic. We can say, okay, we want to be technology agnostic. We want to build this one in Go, this one in Java, this one in whatever, and this one in the framework of the month. Of course, we don't need to be, but in some reasons it makes sense to say, okay, our services are usually in Go, but here we have some machine learning stuff, we build it in Python. So basically, that's a good reason to go for distributed systems, right? And last but not least, we have this co-location sometimes where I say, okay, this service needs to run as close on the edge to the users as possible, so we basically deploy it there. So these are the technical benefits. And they are usually named. If you talk about microservices, this is what people tell you. They say, hey, we built distributed systems, we build distributed architectures for that reason. But actually, that's not the main driver I see why people go for this, or why we should actually even go for this. The main driver is always ownership, right? You want to have this, you build it, you own it attitude, or in the best case, you build it, you run it attitude. And now you would probably ask yourself, but why do we need a distributed systems to achieve this? And the answer is very simple. The answer is autonomy, right? If you now share 3 different teams, one single deployment unit, and one team, messes up something, which is happening on a daily basis even, I would say, right? Then the chances are quite high that this will impact our whole system, and our whole system will probably go down. And this is also the fact where people then don't take ownership, because they say, hey, I will not take ownership of module C as this team because I cannot fully be responsible for it. I cannot take the commitments because I know that if something else happens, I'm out of control, but my part of the system will still go down, right? And what we usually do is we go for these distributed systems to enable teams to work autonomously, and that's a very important part. So we have multiple reasons to go for distributed systems, but in most cases it's for team autonomy. I would even say in 80%, and it's always 80%, right, of the cases I see people shifting into distributed systems, service-based architectures, microservices, whatever it is then, to go for that reason. So when we architect, we usually don't architect for nice technical modules, right? We don't architect to, kind of have all these technical aspects. We usually architect for autonomy these days, right? And architecture is, in essence, at least as my definition, I don't claim that this is the correct one. In essence, it's basically, driven by non-functional requirements. All what we do in architecting things is to figure out what are the key drivers for our architecture, and based on those key drivers, we basically define, okay, how should our architectural style look like, or which architectural style do we want to implement, right? And non-functional requirements are, I usually call them those requirements which make your software non-functional if you don't consider them, because they're usually a little bit underestimated because the naming is very bad. Yeah? So what we usually do as architects is that we kind of get all these non-functional requirements like autonomy, consistency, availability, partition tolerance, CAP theorem, right? We all know that they are always in a trade-off. You never are able to push, all these dots to the very left-hand side. There's always, kind of this trade-off where I say, okay, if I go for availability, I will have a decrease in consistency, and then so on and so forth. And the interesting part is that we often, I see that people do this now, right? They say, hey, cool, yeah, I get it. Architectural is basically driven by non-functional requirements. But non-functional requirements on its own are usually not only technical, right? They are basically a consumption of what we as modern architects need to do these days. We need to understand, okay, what are the organizational constraints? What are the technology constraints? And what is basically the product? What is business and domain? And all three of them together basically define our non-functional requirements. And this is what I usually call the three-folded architect, which needs to keep all these three dimensions, and especially the intersections of those things in mind, right? And what I'm heading in today in this talk is that we usually optimize, as I said, for autonomy, because we want to have autonomous teams, because there's this big hypothesis in our industry: the more independent teams we have, the faster we can deliver software. And also, I think it's a hypothesis from a scientific perspective. It turns out to be somehow right? If you really want to scale engineering, you need to have independent teams that can make independent decisions and so on and so forth. And autonomy is a little bit of a tricky term from my perspective, because it's always considered as a one-side thing, right? You can be autonomy or you cannot be autonomy. And teams are usually always striving a lot for autonomy, which is good. But we need to be very transparent here. Autonomy is not coming for free, right? If you are striving for autonomy as a team, it also comes with responsibility, right? Unfortunately. So you want to be somewhere in the middle, because if you just have, fully autonomous teams which don't take responsibility, then you are in this ops will hate you zone, right? Because they deploy some stuff and, they go home at 5 o'clock and then ops needs to take care of it, right? And if you are in this area where you give full responsibility to the teams but don't give autonomy, they will probably quit you. So you want to be somewhere in the middle. And I don't say that you need to be on the upper part where you say you build it, you run it. So I often have the understanding that especially in Central Europe, that's really hard to achieve. Most engineers don't want to have on-call rotation, which is fair, right? But this also means that we cannot give full autonomy to those teams, right? We kind of need to find a trade-off. If somebody else needs to operate it at 2 o'clock in the morning, then there's someone else, needs to understand, we don't have 52 different technologies how we build our microservice, but we have 2 or 3, right? So if you go for you build it, you own it, or you build it, you care it, whatever it is, somewhere in the middle, it basically also constrains your responsibility. And as I said, this is the first thing which we need to actually even define as an organization, if we go for architectural styles like this. So we have this decision space which we really need to carve, where we on the one hand side have the team autonomy, and on the other hand have, of course, the governance, right? So the less autonomous you want to have your teams, the less responsibility they can take, the more governance you need, and the other way around. So probably if you're somewhere here, then your team autonomy is rather small, I would say, and your governance is rather big. And if you shift, this thing somewhere here, your team autonomy gets rather big, and your governance gets rather small. And you could now expect maybe that in this talk, based on the title, that I talk now a lot about how we can, cultivate architecture by introducing this governance, right? And I talked about this quite a time already, and I think most of us already know this, right? Most of us know about the concept of fitness functions. Most of us know about the concept of figures of merit, so how much requests does a system need to be able to resolve, what's the error budget, and so on and so forth. We know about ADRs and RFCs and processes, which really help us, kind of have a shared understanding of governance. We all know about tech radars, where we see, which technologies should we use, which technologies should we avoid, and which technologies do we need special permission to use. But I would, honestly speaking, focus most on this part now, on this team autonomy part, because this is where we as architects also need to work, right? It's not only that we need to provide the governance, it's also that we need to provide the enablement that those teams can actually work autonomously. And I think we have a lot to do there, to be honest, right? Because as I said before, ultimately, we want to get from there to there, and to do this, we basically need autonomy, and we need well modularization, and end up in something which I usually tend to call this autonomous service-based systems. I call it service-based because I don't care if you build microservice lambdas, verticalized systems, whatever it is. Yeah, for me, it's just a deployment unit in the end. And one thing which we also need to understand when we as an organization make the shift, right? Because we obviously need to make the shift to get more into autonomous teams, is that also the cause of failure is usually shifting then, right? In most situations, the cause of failure in software systems was reliability, okay? 2 + 2 is 4, right? That's reliable. The system tells us 2 + 2 is 4, it doesn't tell us it's 5, right? And we have a lot of investments done that we kind of solve these issues when it comes to reliability, right? We have fantastic test frameworks, we have end-to-end testing, we have test-driven development, we have all these concepts that basically solve the problem of reliability. And of course, we still have the reliability if we move here from left to right, from monolithical deployment units to distributed deployment units, but we get a much bigger problem here usually, and that's availability. And in my workshops, I usually ask the workshop group, what's basically the difference between a method call within a single deployment unit? So you say you have module A, create a user, calls module B, and a method call across the network, right? Who knows the answer? Yeah? Yeah, that's a nice way to say it. I usually say everything, yeah? So you're fully right, yeah? And that's the point, right? Once we start to go for autonomous teams, it's unavoidable to go for distributed systems, and once we go for distributed systems, we need to understand that the complexity increases, right? And you know, if something fails here, then it's probably the error because something failed here, or because this whole network is not available, or basically the network connection is broken, or whatever it is, right? And we all know the fallacies of distributed computing. In a nutshell, everything that can go wrong will go wrong, right? And this then holds us back again from saying, okay, we kind of wanted to have this, but ultimately we now have this big mess, which I showed on the very first slide, right? That the more you go for autonomous and distributed systems, the more you come into a situation where you have big downtimes and things like that. And what we therefore need to understand, if we want to architect for autonomy, we need to optimize for availability. So we cannot kind of just shift this away. This aspect that we now have availability is a big concern when we go for distributed systems. And we often see this. We often see that organizations act like that, right? They say, okay, there's an error here. We have an error somewhere in our loan team service, cannot calculate the loan correctly, or maybe you don't get the loan because, yeah, you should get a loan, but you don't get it, so there's an error, right? And then this loan team goes and says, okay, what's going on? Why does this person not get a loan? Obviously, it should get a loan, right? And it figures out, okay, there's something going wrong on the API, which we call from an external system. Maybe this external system is down. That's why we just, you know, by default say no, right? And then the team starts the investigation, says, okay, cool, there's a problem. Then they go to the landing system and say, hey, landing system, what happened? What was wrong? And they say, okay, we also have somewhere an issue. And basically they need to go down to the whole organization, to the account team and say, okay, obviously there was a problem which basically led to the fact that our system was not properly working. And then they can basically say there and shout to them and say, hey, please fix this because this makes our system not working. And at some point in time, they will fix it. But before they fix this, probably the next error already occurred and the next broken database is there and you know, a misconfigured network and a misconfigured service appears, right? And the point is that we obviously still strive for stable environments. But there are no stable environments in the distributed systems, right? And the sooner we accept this, the better it is for us. So how can we architect with this kind of constraints in mind? Well, it's rather simple. If we have now a situation, and let's jump into a domain, a retail domain, for example, right? Where we have a payment team, takes care of payments, right? So if you buy something in an e-commerce shop, you have to pay it usually, and this team is responsible for it, right? This team then comes to us as architects, or comes to me, to whomever, that's more like a real story, and tells me, hey, you know what? We can currently not execute payments, right? Because our accounting team obviously messed up because we cannot fetch the current users, right? And as we cannot fetch the current users, we cannot basically execute the payment. And the first question should be, but wait, right? Obviously, it's not the accounting team service. Obviously, it's first of all the fault of our team, of our payment team, that the whole payment service goes down if we cannot fetch users, right? So we should probably, first of all, kind of build the system more resilient and, throw back some meaningful error or whatever, but we should isolate the problem, yeah? That's the first thing, but probably that's not enough, right? If the account service goes down every 2 days, right, and you cannot do a single payment, then probably your business is pissed and you need to involve, right? So you can, for example, introduce a simple cache, or you can say, okay, we do event-driven reactive architectures and, introduce a Kafka topic and basically consume whenever a user is changing and build up our own read model, our own projection there, right? And then when the account service goes down, we don't actually care because we have all the data which we need during runtime available, right? We have other complexities that this data can get stale and so on and so forth. We know this, right? But in the end, we build our system for what we're striving for, autonomy, right? And we not only strive for this on the organizational level, but we also strive for this on the architectural level. And we also need to do this from the other perspective. So maybe we have another team, which goes wild, which DDoS us, which, sends a lot of requests, which we usually don't expect, and which basically brings us down, right? Again, we need these resilience patterns here. We need to say, okay, we have probably a load balancer, a circuit breaker, simple caching, whatever it is. But we need to architect for those chaotic environments, right? We work in autonomous organizations with distributed systems for the only reason that we kind of enable autonomous teams. So we basically also build our systems in a way that we are autonomous from the outside. So we need to architect for those chaotic environments because they are unavoidable, unfortunately. And what I tend to do there is that I want to have my autonomous services, my autonomous teams as autonomous as possible. And I know it's always a trade-off, right? But for example, one very interesting aspect is that you really need to start dancing with the beast, right? You really need to embrace this chaos, and we have good techniques on this, right? As I said before, we have a lot for reliability. We also have a lot of things for availability these days. We can do some game days, right? We can say, okay, we shut down the database now, we shut down the network, we shut down the service, and we see how the system reacts. And I want to have my production not always running smooth, because I anyway know it will not always run smooth. But if it's not running smooth, I want to be part of it, right? I want to sit with my whole team there on a Wednesday at 2 o'clock after lunch and say, okay, now we do a game day, right? I don't want to be waked up at 3 o'clock in the morning, being fully crooky and saying, hey, something's not working because obviously the database went down. How can we deal with it, right? And that's exactly what I mean with embracing chaos. Right? And the thing is, a system that can run in a stable environment can run only there, right? But a system that can run in a chaotic environment can obviously run everywhere. So we need to embrace this architecting for chaotic environments. But if you took a look at this, probably you spotted another elephant in the room there, right? Because we said, okay, that payment went down because some other team was not able to deliver their stuff. In our case, we say, okay, the payment team is again shouting and saying, hey, we cannot do a payment because the payment execution is not working because the payment gateway team messed up something, so we cannot execute the payment, right? And then you should probably ask yourself, but wait, why do we actually even have this, right? Why do we have a payment team that needs to go to a payment gateway team to basically fulfill an end-to-end need, to fulfill this whole end-to-end verticalization of a business demand? And this is why you usually say, okay, let's go for end-to-end verticalization, right? Let's say, okay, we have one payment team which takes care of payment from end to end, right? Because then it makes the most value and then it can take most responsibility for this, meaningful business demand. And then, of course, I know the answer is cognitive load, which is fully fair, right? People say, okay, no, that's too much, right? We cannot do the whole payment, and we cannot integrate all the payment gateways with 6 or 7 people. These people, are just bloated by the end of the day. But still, I think the answer would probably in that case, and we did this all real-world example somehow. We did this and say, okay, then let's cut it still vertical, right? Let's say we have one team which is taking care of SEPA payments and interacts with SEPA payment gateways, and we have one which takes care of credit cards and interacts with credit card payments, right? So we need to strive for this end-to-end responsibility, because then we basically can assure also this autonomy of those teams and them taking responsibility, because they kind of get this vision. They say, hey, we as a team are responsible that people can pay with the credit card, right? And of course, we have dependencies between these verticals, right? Because we often discuss this then, yeah, in the end, software architecture is all about horizontals and verticals, right? And of course, we will have dependencies in there, right? But again, we probably need to resolve those dependencies, right? And we need to find ways, which I showed you before, resilience patterns to get these dependencies. And I think Nick Thune was here yesterday, and I think he also explains it very well, right? That we basically, our job is to find verticals and horizontals and then to decide on one of those two directions. And especially, I think, with this end-to-end responsibility, you spot this very well. Because you have something which I usually tend to call the customer journey entity data mismatch problem. And it's very obvious if you think about our architectures these days, right? And we invest a lot in verticalization. Then you usually have entities and you usually have customer journeys. So your entities could be users, accounts, transactions. And your customer journeys are, let's say, payment execution, user onboarding, and fraud detection. And the payment execution obviously needs a user, probably also needs an account, probably even needs a transaction. User onboarding obviously also creates a user, probably even does some stuff with accounts, and fraud detection needs accounts and transactions. So we see there's an overlap, right? And that's the whole problem of our horizontal versus vertical discussion. There's an overlap. We cannot say we build fully independent verticals when we share usually entities across those verticals. And again, that's a challenge which we on a software architecture level need to solve, or which we on a software architecture can solve. That we say, okay, somebody needs to own accounts. That's the first thing we need to do. Clarify ownership. Who owns accounts? Good indicators are usually those who create them initially, or those who obviously work with them the most. So let's say we figure out, okay, this vertical owns accounts, right? And again, if this now goes down, our other vertical is not working. And we talked about this already, and if you know me, you know that I talk a lot about event-driven architectures and reactive systems, but these are usually good answers to this, right? Instead of introducing a cache, again, introducing an event stream and building up on read models, which make our lower part of the system very resilient because we are not affected anymore if the upper part of the system is not working anymore. And this is actually what we also should keep in mind after dealing with chaotic environments, having end-to-end responsibility in mind. And this end-to-end responsibility always, as I said before, comes or is unavoidable to have dependencies in, right? So we usually trade in this end-to-end responsibility our dependencies with decreasing cognitive load, right? If we would build everything on our own as teams, right, we would first of all have huge duplication, and we would second need a lot to maintain, right? Because we say we don't want to have anything to do with the outside world. But we want to have something to do with the outside world because it gives us important features, right, which we don't want to reinvent on our own. So in the end, it's always, this trade-off, right? And that's basically where we then introduce team topologies, or where I find team topologies very, very useful, just as a terminology, that we say all the teams we have there, right, beside the stream-aligned teams, their own goal is basically to decrease cognitive load, to carve cognitive load out of the verticalized teams, that we can span the vertical as long as possible, because we figured out if we don't do this and if we make intersections between those verticals, it usually is very painful. And that is where we introduced then complicated subsystems, right? Where we basically say, okay, let's make the fraud check in a complicated subsystem. And there we basically treat those complicated subsystems like we treat our customers, right? As customers of our system, they should treat us as their customers, because the only reason for existence is that they make our life easier as stream-aligned teams, right? And what we of course need to know then, if we have dependencies to, for example, complicated subsystems, is we need to know the availability, we need to know the mean time between failure and things like this. So we need to, unfortunately, talk about the nines when it comes to architecting. We need to understand, hey, how many nines does this system give us, right? How many nines do we get from the fraud detection team? If they say we give you 3 nines, then they have a downside of 9 hours. Probably too much for us as a payment team to say we are not able to take payments for the next 9 months. So, and I need to look a little bit on the time, but I usually ask then the audience, or also in the workshop, the people, can you actually achieve a stream-aligned teams with 4-9 availability if you have just 3-9 availability on your complex subsystem? And of course you can, right? That's our job, that we ensure that this is working, right? Because we say, okay, we introduce, for example, some things like easy rest schedulers, right? Which then try again and say, okay, we did the payment, or we will do the payment for you. Actually, we didn't do it, but we will do it in the future at some point in time, right? But if the system, for example, has 5-9 availability, we can just skip this, right? We can just say, okay, who cares, right? The system is down for 5 minutes a year, right? We can just say, give the user error and tell him that he should probably retry it again. Sufficient enough. And this is what needs to drive our architecture. And the same goes for platform teams, right? As I said before, all these non-stream aligned teams, at least from my understanding, have the only goal to reduce cognitive load from the stream aligned teams, to make us span the vertical as long as possible. And again, we need to ask them, hey, what is basically the mean they are giving us, right? What do we get from them? What are the SLOs? What are the SLRs? And so on and so forth. And you probably also know Vladik. I know him quite well, and I like him a lot, and I like a lot the stuff he publishes. And he usually comes up with this very useful kind of definition of dependencies, which gives us, at least from my perspective as a community, a very clear discussion point. Because not every dependency is bad, right? Software is dependencies, right? We just need to figure out which ones do we want to avoid. And you probably know it, but he says basically these are the 3 main aspects: strength, distance, and how often does it change, volatility. And this is the pain of dependencies, is the multiplication of this, right? And as you know, in multiplications, only one factor needs to be 0, and then the whole multiplication is 0. So he says, if we don't have long dependency between dependencies, right? Long distance between dependencies. If you have a dependency within your team, right, then probably the dependency is not that bad as if you say, I have a dependency from here to a team sitting on the other side of the world, right? The same goes for volatility. If you have a dependency to something that never changes, right, who cares? And that's exactly the point. But we need to understand this. We need to think about dependencies as first-class citizens, and I like this term of dependencies as a service. We really need to treat them as any other external dependencies which we had, even if it's, kind of in our organization, or if it's kind of in our software system landscape. And last but not least, then I'm really finished, is the last point I usually like to bring in when I talk about cultivating architecture is that in most cases, we don't start from the greenfield. And that's interesting, right? That's why it needs us, right? Everybody can build a system from the greenfield, right? we are usually coming in situations where you have some legacy stuff, right? And then we could talk about legacy decomposition on its own, but what usually turns out to the best way to decompose legacy monoliths is inverse convoy maneuver, right? To say, again, from an organizational perspective, you are the SEPA payment team, right? You own payments. And we know there is still some part left, unfortunately, in the monolith, right? But you're responsible for it now, right? And if you as a payment team, want to ensure that you're not running on such a shared platform like a monolith, right? You're still responsible for it. So probably those people will start to carve out the things which are important to carve out, right? So inverse converse maneuver, so triggering monolith decomposition from an organizational perspective is probably the best thing we can do these days when it comes to legacy decomposition. And what we usually then have is, of course, we have something like this, right? Some big monolith, and we need to carve out some stuff, and this big monolith has a lot of readers and writers, sometimes even directly on the persistent, sometimes at least on service level, and we basically take this logic out. That's the easy part, right? Because you know the hard part is to take also the data out, right? And we then introduce APIs, and then we say, okay, cool, we did it, we shift everything over now, right? And then we can be sure that first of all we need a downtime here, right? Because we probably need to turn the monolith down to take the data out, migrate it over, pipapo, right? And the second thing that will for sure happen is, that something is not working, and the API probably cannot do some write access or read access, and we need to migrate this reader who has a problem back, right? And we of course cannot just migrate one thing back, we need to migrate everything back. And to be honest, right, then we need to fix this, and then we kind of can migrate it again, and then we have again a downtime, and we do this at Friday at 5 o'clock in the afternoon when everybody is super happy to do this, right? And these are exactly the situations that, honestly speaking, give me a heart attack, right? This is not what I want to work on anymore, right? I don't want to have these shitty migrations anymore, right? Where you do these big bangs, and we all know that big bangs always only end up in big bangs. And what we usually should do is that we say, okay, we introduce this API taxonomy, we introduce a new database structure, and we basically, again, can use the means of event-driven architectures to say, okay, we CDC the user fraud data out of the legacy system, build up, kind of a read model on the left-hand side, and basically can at least shift readers over, right? They can read now from both persistences, right? But usually it's very hard to just shift readers and then 6 months later shift all writers. Usually teams own readers and writers, and teams want to, shift everything over. So we probably need to do this circle even in the other around, right? So if you write into the new persistence, then you probably just also trigger an event and keep the old persistence in place. Then you can kind of shift writers and readers. And of course, there's a lot of complexity in this picture, yeah? You all know it, right? Eventual consistency, all the things. But in the end, it gives us an easy way to transition from left to right, right? It gives us a possibility that if this writer has a problem, and we figure out this has a problem, and we figure this out on Friday, when we usually figure out problems, we just say, okay, guys, let's shift it back, right? Let's go on weekend, right? And let's get back on Monday with a fresh mind and fix it, and try it again, right? And this is how I want to have migrations done, right? And at some point in time, I have migrated everything over, and I can just shut down the old legacy monolith, and I have even already the events which other services can consume. And this is how I want to have migrations done, right? I want to get rid of this, migration NCNT, of this downtime NCNT, right? That you basically have a very, very safe way to kind of deploy your things. And this is just one example, right? These zero downtime migrations. But there's canary releases, there's dark lounging, there's AP testing. There's so many things which are useful, which we can use to basically decrease the NCNT for developers to kind of make changes in the end, right? And there's also the scientist pattern. I often bring this in my workshops because I find it so useful, right? And it was introduced by GitHub a while ago when they did a really big change, right? Where they said, okay, we basically now shift the logic, how we merge pull requests, right? And of course, that's the core of the essence, so to say. And what they did is they introduced a Git library which is called Scientist, and you basically just define a scientific, or I would say, how do they call it? A science example. So you act as a scientist and you start to say, okay, 5% of my merge requests now go against the new code, but they still go against the legacy code, right? And we basically just compare the results, right? We throw away the stuff from the new service, but we compare, is it equal to the stuff from the legacy service, right? And they did this, and they have a great blog post where you can read up further on this, but basically they just tracked in which situations does the new logic kind of, not go hand in hand with the old logic. And they had even possibilities to, based on this, figure out the performance difference to say, okay, our new system is much more performant than our old one. And what they say to the developers, we will just, make the shift once we don't have a disagreement, so a disagreement between the new and the old system, how the merge afterwards should look like in 24 hours, and at least with 10 million comparisons. And this is how I, as a developer, want to work, right? I want to be safe. I say, hey, cool, I can go do this change. I have the environment to test it out, right? And I don't need to deploy something, and then I'm running out of the office because I don't want to be here anymore, right? And that's exactly the point. And that's what I mean with architecting against change anxiety. And I think that's very important. So let's come to an end. Let's quickly sum up. So I think I touch point a lot of topics, and this is because of the fact that I talk a lot about these ideas, and I usually then, shuffle different ideas together into something which I think makes sense for this audience, hopefully. And in the end, I think I wanted to make the point that you as an architect, you are driven by non-functional requirements. And those non-functional requirements are not only technical, yeah, they're threefold. You need to understand the organization, you need to understand the product, right? And you need to understand the technical means to basically come up with good architectures, because in the end, it's a trade-off. Your architecture is a trade-off of all those non-functional requirements you can optimize for. And in most cases these days, we architect for autonomy, right? And it's not that's not true for all cases, right? There are organizations where you don't want to have team autonomy. Fair enough, right? But in most situations, you want to have it, right? There we first of all need to understand what kind of autonomy do we actually want, right? At which scale do we want to have autonomy, right? And based on this, you basically design decision space. And I think what's very important is that we as architects work on enabling this team autonomy. And to do this, we need to understand that availability is a very crucial factor once we shift into this direction. And I showed you just 3 examples or three patterns I usually use. Is to architect for chaotic environments, right? To architect for end-to-end responsibilities, to architect for complicated subsystems and platforms to kind of decrease the cognitive load from these teams, and last but not least, to architect for dependencies as a service, with an architecting for change anxiety in mind within the teams you're working with, right? And if you follow those approaches, at least from my opinion or from my experience, it makes things a lot easier to kind of shift into this mindset of architectural autonomous teams. And it hopefully also brings us to the goal which we raised in the first slide, that we safely and sustainably reduce the lead time to thank you, because I guess that's why we're all here for. And say thanks a lot. I hope this was useful.
Yeah, we have no time for questions, but David is right there, so you can go up and talk to him. I'll see you here in 20 minutes about embracing evolutionary architectures by Vivek, who's sitting right there. Yeah. So thank you again, David.
You're welcome.